Hello, everyone. Welcome to IMSC A82 Network Flow and Graph Theory class. Today's our lecture to cover the so-called maxima cardinality matching and maxima weighted matching, solving them using Python library from NetworkX. To start this notebook, we import some of the necessary library, the NetworkX library, the matplotlib, pyplot library, and also the numpy library. And the first line here represents all the graph. Once I submit the plot show, it will automatically show without waiting on that cell. So first we tried the maxima cardinality matching directly from NetworkX reference manual and say we're going to define certain graph with using their edges, and then we solving a maxima matching and print it out. So for this graph, only two matchings possible. Then we turn our attention to our example we discussed in the lecture 14 and 15 today. So first one is we're using a example 1 from lecture 14, the end of lecture 14. We walk you through this example in class, in the lecture, step by step, manually. But here we're trying to see if the Python library from NetworkX can solve this problem. So I tried it for both formatted inputs, since this is a undirected graph. I tried it for just define one direction and for this undirected graph, or I duplicated the link, the edges for each direction, and following the reference manuals as an example. But instead of just print it out, I put it into a matched edges list. Okay, right here, matched edges list. So you can see that, and then we print it out. So as our network example, we have 5 matches. But this 5 matches is slightly different, actually very different from the one we got in the manual example in class. So I'm going to decide to visualize this. I'm going to put in all the edges which is within this match the edge. I'm painted red, and rest of them painted like a lighter gray, so you see the difference. Also, the width are a little bit different, either 3 or 2. Then I specify the node position and for this, and so that I can mimic whatever we have in the lecture videos, lecture handout, and line up all the node properly in certain position. Then finally we can draw this, and I'm going to using dark green as my node color and white as my node font label, and node size is 700, and node color is kind of dark green, and the edge color, which either red or light gray, edge width is either 3 or 2. So you can see that this is the this first example solving our class handout example. And you can see that even though they have exactly the same number of matching, the cardinality is the same. However, the the matches are different. So kind of changing the note a little bit. So I'm giving them a hint. Okay. So the first 1/5 and 1, 2, 2, 5, and giving some hint to begin with. And this example, try to both, and both give it exactly the result. So using the first way is probably already sufficient without defining the path from either direction. Same thing, I'm going to solving using the maximum matching library from the network X. I stored this result on match the edges too. Okay, then we'll print it out. After I print it out, I find out this example with some hint, which is rearranging some of the arc sequence in the presentation. In the definition, actually create exactly the same result as our class example in the handout. Similar trick using to color the matched edges, match the arc with the blue, and other ones with the lighter gray. And the matched edges has a width of a 4, other ones has a 2, so you can see the result using the same routine. So this solution is identical to the handout result, optimal maximum cardinality matching. So we start to understand this method, the routine, maximum matching routine in the network X could have produced alternative optimal solution, which is frequently happened in the maximum matching. But with a slightly different rearranging the arc sequence, in the definition, in the graph definition, we can get a different alternative solution. The third example I'm trying is the example 2 in our handout from lecture 15's handout. And for this example, we know that our solution has maximum 4 possible matching in this graph. We do the same, defining the graph first, and then using maximum matching for the third graph we define, and we're getting the result is 4 matching, actually identical to the ones we presented in our lecture video in the handout. For this, I colored matched the edges with the green, the other ones with the light gray. Matched edges has weight of 4, other one had 3. So you can see the different result as well. Okay, so here are for example 1, try 2 different ways. Example 2, I try another one. So we all have achieved the maximum cardinality matching with it. Actually, in our handout example, and the fourth match is basically 4 and 9 instead of 4 and 10. But either way, they reach the same cardinality of matching. It depends on how you grow your augmenting path. Continue on, we start talking about our third example in lecture 15, and trying to solve for maximum weighted matching we talk about in lecture 14 and 15. Similar things, we try the example directly out of the reference manual from Network X on the maximum weighted matching, maximum weight matching. And then we tried example 3 presented in our handout. Okay. For that, we each one of the arc actually defined with a certain weight and for the matching. So we defined a list of edges, and then we're using this list to define our graph, which is the G right here. Then we solve for maxima weighted matching using G, and the result is stored in this. So here we can actually match. Okay. I'm sorry. So this is the three matches. We have 2, 6, 3, 5, and 7, 1. In order to visualize it, we did the same thing. So we first color all the matched edges with the blue and set the edge width with a 4 if it's in the matching. Otherwise, we set it to 2. We can do this in 2, for example. And then we're going to print the result, and again, one more time, and plot the graph. So this is the graph actually we see. Okay, and total 7 nodes, and maxima weighted matching is 2, 6, and 1, 7, and 3, 5. And the total weight for this matching is 11, okay? And I think 4 plus 4, this is a 2 with the 4, plus the 3, 5 is 3. So 4 plus 4 plus 3 is 11. Just for the heck of it, I also tried this example using the minima weighted matching. Instead of finding the maxima weight for matching, see if I can find the minima weight for matching. So I run the Network X minima weighted matching algorithm. Okay. And color the matching, arc with the red with a weight of, let's do 4 again. Okay. And then, and the width with the matched edge is 4. The width for the unmatched arc is 2. So see if we can get the same similar result. Zoom out a little bit. Okay. And with the minima weighted matching, so 2, 4 is 3, 6, 7 is 3, and 3, 5 is 3, 2, 4 is 3, and 6, 7 is 2. So total weight for this match is minimized with a total of 8. So maxima is 11 and minima is 8. So this is pretty much the result we're getting for either maxima weighted matching, and the cardinality then changes 3, but the total weight for these matchings are either minimized or maximized. All right, so this is pretty much a quick and easy tutorial. I do have another source code directly manually implement all the maxima cardinality matching. I was using a separate lecture video to demonstrate that, the use of that source code. But here, just giving you a very quick and easy way to find out the either the maximum cardinality matching or the maximum weighted matching and the minima weighted matching. So you can see that in the minimum weighted matching and the maximum weighted matching, the cardinality didn't change. However, the cardinality is maximized, but the total weight is either minimized or maximized. All right, we conclude this short video really quick on matching, non-bipartite matching problem. We will have continue more of the example coming up for the matching problem. We'll see you in the next lecture video.